Hi friends, today we are going to see a protocol called as RIP, that is Routing Information Protocol, which is belonging to a category of distance vector routing. So distance vector routing means each node will be transferring its own routing table to only to the nearest neighbors. So the nearest neighbors in turn transfer their routing tables to their nearest neighbors. Likewise, it will be a chain of network. So here what happens is all the nodes in the network will have a incomplete information, but as a whole of a network together, everyone will have a complete information about the entire network. So this is what this distance vector routing. So one of the example protocol is the RIP, that is routing information protocol. So in this simulation we have seen we are going to see on network simulator 3 how RIP is implemented with the three options called as split horizon, no split horizon and Poisson reverse. How that is enabled, and through the routing tables we could able to find out how these three things have occurred in the RIP protocol. Now over to the simulations. Hi friends, so now we are going to check about split horizon, no split horizon and Poisson reverse in RIP. This is what we are going to see in this lecture. So let's say we have a router R1, a router R2 and a router R3. So assume that all are connected to each other, and here is the one IP address 10.0.1.0/16. So this is an IP address, this is a server. Okay, so now in this case, now this is how the way the thing works. Now in case the first condition is no split horizon, no split horizon. In the first condition, what happens here is, now from this information the packet comes here. Now this R3 will send the packet here and R2 will send the packet here. Now for example, if this packets comes like this, R3 sends to R2, R2 sends to R1. Now because of some reason this packet got broken. So this packet from R2 to R3 got broken. So now what happens is R1 will be having a routing table update to R2. So routing update to R2. Similarly, again R2 will be sending the routing update. So because of this packet failed, this link failed, the R1 and R2 will be engaging in a infinite loop in RIP. So this is the problem with the no split horizon. So this is the issue with no split horizon. So this case is infinite loop. This is one of a normal condition where it can able to engage in an infinite loop without giving any useful information to the rest of the network. Now in case of second condition, here is split horizon. So how here it happens is, now again we will take the same thing, R1, R2 and R3, and here is the network here. Now here this how the it goes. Okay, so now from this 10.0.1.0/16, so from this the routing updates comes here. Okay, so from this the routing update comes here, and from this the routing update comes here. Now for again the same condition, this link fails. So this link fails. Now in this case, this R1, if it is enabled with split horizon, if this split horizon, if it enables, R1 does not send anything to R2, because it indicates that because already the link is broken. If it is split horizon is been maintained here, this packet won't be there, and this won't be engaging in a loop, won't be engaged in a loop if split horizon is enabled. Okay, so but in the no split horizon, what happens is the splitting won't happens here. So because of that there will be a infinite loop. This is on split horizon. So third condition here is we call something called as Poisson reverse. So this is something called as Poisson reverse, otherwise we called as split horizon with Poisson reverse. split horizon with Poisson reverse. So how here it happens is, now here there's an interesting thing here. In this case, again we have R1, we have R2, and we have R3. Okay, now this thing network here, this thing here. So 10.0.1.0/16. Okay, so now for example, this routing update comes here to R2, and from R1 the routing update comes here. Okay, so now the split horizon is enabled here. Now this link got failed, so this link fails here. Now in this case, when it fails, here happens is, after it is failed, this will become 16. 16 means the infinity. So in RIP protocol, infinity is the maximum cost. Infinity. So the maximum cost is infinity here. So that means 16. So in RIP, 16 is the maximum cost between any two links, so which will be considered as infinity. So R1 is unreachable to the node R2 because the link will become 16. That means the link cost will be 16. So which is unreachable. So in that case, the Poisson reverse will ensure that the loop should not happen between the router R1 and R2. So that's why it is Poisson reverse. So to recap, we have no split horizon. That means it will go involved in an infinite loop. Split horizon, there could be a chance from R1 to R2, but split horizon with the Poisson reverse will never happen because of the cost involved there. Clinic. Today we are going to see one protocol called as routing information protocol, which we shortly call as RIP, which is based on distance vector routing protocol. Okay, so we have some theoretical concepts, so we will be seeing in between how the theoretical concepts were been implemented, and now we will go into the source code, which is in NS3. So we are going to define using design this network using network simulator 3 network simulator 3. Okay, so now consider this example where we have SRC node is the source node and DST is the destination network, and we have four routers A, B, C, D. Okay, now all the networks have cost 1. Cost 1 means between A to B, A to C, B to C, and B to D we have the cost 1, except the direct link C to D, which has cost 10. So C to D is 10. As we know that distance vector routing protocol, the shortest path only it will be followed. So based on the distance, the shortest distance, the source will be routing the packets to the destination. Now in case if SRC to destination, the what is the optimal path will be SRC A, C, D and destination. In case C to D is 10, so which is the total path will be 1, 10 and 11, 12. So it will be 12. So it won't be. So instead the path will be SRC, A, B, D. So that's how the way the path will move. So there are two paths here. So two paths, namely SRC will be 1, then A, then B, then D. So this will be, if you see the cost here, SRC to A will be 1 plus A to B will be 1 plus B to D will be 1. So which will be equal to 3. Just 3 is a cost. So in case another path, so SRC, then A, then C, then D, then finally DST. So in this case, when we see the path, SRC to A is 1 plus A to C is 1 plus C to D is 10, then to the destination. So D to destination is also 1, then so totally if you see the path will be equal to 12. So this is how the way thing goes. So always the RIP network will always follow the shortest path. Okay. Now in this case what happens is A, B, C, D are the RIP next generation routers. A and D are configured with the static addresses, and SRC and DST will exchange packets. So source and destination, that's what we have, SRC and DST. Now in this network what we are going to do is, after about 3 seconds the topology is built and echo reply will be received. After 40 seconds the link between B and D will break. So for example B and D will break, that means this B and D path will be broken, in that case causing a root failure. After since RIP the failure will be recovered after some point of time. So after 4 seconds, that is at 44 seconds from the failure, the routers will recovery from the failure. So in that case, we use the split horizoning should affect the recovery time, but it is not. See the manual. We will see that what is a split horizon. So what does it mean? Now in this case, after some point of time, what happens is, since B and D is broken, so obviously SRC A C D will be the packet, will be the transmission of the data from the source to the destination. So in that case, obviously the C to D has to be built for 10. So the cost will be 10. So that's how the way this network will work. Now let's see how this has been implemented. Now as usual, we have this core module, CSMA module, all these modules have implemented. Now we have the tear down link. So tear down link, first thing is we have a tear down link. So that means the downlink. So we have a function. This is a function. The function will be called. So what the parameters are: pointer to node A, pointer to node B, interface A and interface B. So based on this, the set down. Set down means interface A and interface B will be shut down. That means what? Between node A to node B, whatever the interface A and B, that will be set down. Set down means the link will be down. So this will be called at the 40 seconds as per the program. Okay. So now we have a main function. So we have this bool verbose equal to false. So this verbose we will make it true and then see how the ping packets are working and print the routing table. So we can print the routing tables also. So by default it is given as false. So whenever we want to make it true, then we can do that. And show ping. So ping packets we want to show true or false. All these things by default they are given as false. Now the split horizon, Poisson reverse. So as we have seen, what is the split horizon? So we are using a method called as Poisson reverse. So we have three methods here: no split horizon, Poisson reverse, and split horizon with Poisson reverse. So that's what we are using, these three things. Now we have add value here. So verbose mode, if you want to enable, we can use verbose mode. Then print routing tables we can enable. Then show pings we can enable, and split horizon strategy. So three split horizon strategy we can make use of. So we have no split horizon, and Poisson reverse. So these are the three things that we can make use of. So we will see how to use all these things. So now log component enable. So what are the different logging we are going to enable in this? So we are going to enable log RIP simple routing, RIP IP version 4 interface, ICMP version 4 L4 protocol. That is on the layer number 4, which is nothing but a transport layer. Then IP version 4 L3 protocol, which is on the network layer, ARP cache address resolution protocol, and ping. All these things we are going to enable the logs. Okay. Now we have the macros here. So if split horizon equal to no split horizon, then we are calling this no split horizon as one of the enumerated values or the macros. And similarly, if split horizon equal to split horizon, we will be calling the split horizon. So this is part of the RIP next generation. Similarly, if we use not split horizon or no split horizon or split horizon, then we go for a Poisson reverse. So this is what we are going to use in case of Poisson reverse. So now, as usual, we are going to create the nodes. So how many nodes we will be creating? We will be creating a source node, destination node, router A, router B, router C, and router D. So we are totally creating SRC, DST, AB, CD. Now we are going to, as per the routing table of the RIP. So we are connecting SRC to A, then A to B, A to C, B to C, C to D, B to D, and D to DST. You can see here, as per this same thing, SRC to A is connected, A to B connected, A to C connected, B to C connected, B to D connected, and C to D connected, and D to DST connected. So all these links have been connected here. Now after the connection, so we are just creating a routers ABCD, and we are creating nodes, source and destination. So source and destination are the nodes, but ABCD are the routers. That's why they route the packets based on the lowest cost metric possible. Okay, now we are going for creating a channel here. So now since it is a CSMA, we are going to have a carrier sense multiple access. So because it is between routers to routers, we want to establish a higher data rate channel. So we use a CSMA helper. So here we are using 5 Gbps and 2 millisecond delay, the data rate and the delay. Now we are going to define a network device, net device container. So as what, if you don't know what is net device container, please follow my some of the other videos. That what is a net device container, I have explained detailedly in the in those sessions. Maybe I'll just give the video link in the description window. Now we create net device container NDC 1, 2, 3, 4, 5, 6, 7. So for that we create the net 1, net 2, net 3, net 4. So that means what? Net 1 means, so this is net 1. So between source to the router A, we are creating one net device container NDC1. Similarly, for net 2 between A to B, we create NDC2. Likewise, up to NDC7, we just create totally 7 net device container 1 to 7. Now we just go for RIP routing here. So in the RIP routing, we exclude some interfaces. So the router number A, the first thing is excluded, the interface excluded, and router number D, the third interface is excluded. Here just to exclude, not all the ports to be included. Some interfaces we can exclude also. So we just exclude that. And if you want to set the interface here, interface metric for node number C, it is 3 and 10, and for node number D, it is 1 and 10. As we have seen that the cost between C to D, we want to make it, instead of 1, we want to make it as 10. So that's why the interface for C is number 3 at a cost of 10, and the interface of number D is 1 at the cost of 10. Now we use the routing helper here. So list RH routing helper. So we use RIP routing 0 here, and we just set the internet stack helper. That means for all the routers we want to provide the network connectivity. For that we create an object called as internet. So in the internet we just create IP version 6 as false. That means we are going to focus only on the IP version 4 addressing. Similarly, in this internet asset routing helper list RH, we just sent the list routing helper to all the routers. That's what we are installing everything on the routers. Now in case internet nodes, so this is the internet stack helper. Now in the internet nodes, here we install it on the nodes here. So we are installing it in the routers. Now we are installing on the nodes. Routers means ABCD, nodes means SRC and the DST, that is source and the destination. So now we are assigning the IP version 4 addresses. So we just create an object called IP version 4 address helper. So where we can see that 10.0.0.0, 1.0, 2.0, 3.0, 4.5 and 6.0. Now in everywhere you can see that this NDC1 we set the IP address, NDC2 we set the IP address, NDC3, NDC4 like that. So NDC1 is between source to the node number A. This is for NDC1. And finally NDC7 is 10.0.6.0. So this NDC7 here is between D to DST. There is a destination. So this is what NDC7. Okay. So this given 6.0. Whereas in this case here, this case here is SRC to node A. So sorry, router A. So this is what this 10.0.0.0. So now we are going to focus only on this IP address as well as this IP address. So these two only we are going to focus on. Now we have already mentioned in the problem that we are going to have a static routing on the static addresses that the nodes are using. So you can see that the routing protocol here, the default route given us, the cost is 1, 10.0.0.2, it is 1. That means this is from SRC to A, and 0.6.1 this is from D to DST, which is also the cost is 1. So this static addressing cost is only 1. That's what here is given here as a static routing. Now if print routing tables, that means if we enable print routing tables, which is by default value as false, that means it's a false value. But if I want to give a true value there, I can able to enable. In case we want to make it true, I can use this way. So this becomes true now, because not of false will be true. So in that case I can make it true. Now by default it is false. So this way, in case if I want to print it, then the routing table ABCD will be printed at the time number 30 seconds. After 30 seconds, again the ABCD will be printed at 60 seconds. Then again at 90 seconds it will be printed. Why it is printed is, we can check the routing table, that how the routing table changes after the link is failure, because we are going to have a link failure between B to D. The link is going to be failed. After failure, how the system recovers from the failure and how it takes alternative path. That's what we are going to show you on the RIP. Okay. So for that we can enable the 30 and 60. You can see that it will be a normal routing table, but whereas in the 90 seconds, the routing table will be completely changed, because the link got failed, and after that the link got re-established, and the cost becomes, instead of 3 or 4, the cost becomes 12. So that we will be seeing it. Then finally we are creating an application with a packet size of 1 kilobyte, that is 1024 bytes, and we are going to have a ping application with a ping IP version 4 address. And again show pings also we are given as false, but in case we want to enable true, then we can enable. So let me make it true here. True means not of false will be true. So I will be giving the true value here, so that you can enable the verbose mode. Then we start the ping.install in the SRC. Start from 1 to 110 seconds. So totally I want to run the simulation for 110 seconds. Then we establish the routing, the trace file, that is ASCII routing. Again, if you want to know about this ASCII, all these things, I have just given a video below. You can check it. Similarly, packet capture is for Wireshark. So we want to create Wireshark for all the routers and the nodes, so that also we can able to print it. Now finally at schedule 40 seconds, at 40 seconds tear down link. That means we call the function tear down link, which we already given in the beginning, between node B and D on the interfaces. So B interfaces is 3 and D interfaces is 2. So that's what it will be. Now run the simulation, destroy. So the simulation will be stopped at 131 seconds. So yeah, very detailed application here. So we are just going to run this example. So let's say how to run this example. So I'm just opening from the beginning. So I'll just open a terminal here. So what do I do is cd ns all-in-one -3.40 / ns -3.40. So now here I have the application. So now I have just opened a new terminal and I am running the command /ns3 run scratch rip-simple-network.cc. So now once you see that we have the ping application installed there. So the ping packets have been shown here, and see the total packet loss is 39% packet loss, where 66 received. So inside our program we have made the link down. So during the downtime there was the packet loss because the ping packets were never working because there was a failure there. Actually RIP network doesn't come recover from a failure. So now what we do is we print the routing table there. So we have one place where we have a print routing tables is disabled, so we will enable that. So what we do is here is a print routing tables. So this value is declared as false, so we'll make it true by adding a exclamatory mark there. So there is a not of false will be true. So now I will be running the program again. So when I run this, you can see there the routing table got printed up there. So you can see the first routing table. So the routing tables are printed for ABCD routers only. So the nodes were not printed, only the ABCD routers. You can see that node number 2 is the router number A. You can see the metric is the metric parameters. You can see 3, 2, 2, 2, 1, 1 like that. So between the destination to the gateway, and we have the metrics is 3. So maximum link is 3 only. That is the maximum cost is 3. And similarly for node number 3 you can see A, B. Node number 3 is B, the B router. You can see that's also 2, 2, 2, 1 only. And similarly we can see node number 4, that is a router number C, that is also 2. And node number 5, that is a router number D, that is also true. Now after that again we have some ping packets. Then again we have node 2, 3 because we are printing the routing table 3 times, 30 seconds, 60 seconds, 90 seconds. Now the 60 seconds again there also you can see the matrix says this 2, 2, 2, 1, that is node number 2. And node number 3 also 2, 2, 1, 1. And node number 4 also 2, 2, 2, 1, 1. And node number 5 also 1 and 1. Okay. Now afterwards again that thing happens. Now you can see this is the 90 seconds. Now node number 2, the node number 2 you can see the cost here is 12. So now here what happens is the link is got down, the link failure. Because of the link failure, the RIP network follows the C2D path. C2D is nothing but the cost is 10. Already 1 plus 1, so the 12 path is followed there. This is for node number 2. So 10.0.6.0 to 10.0.2.2 is 2.2 is nothing but node number A, B. It is B, and 6 is node number the destination. So that's how the way 12 packets, 12 is the path. Similarly for node number 3 you can see that is a router number B. Again it follows 12 path, 12, and somewhere you can see the 16 also there. So the metric is 16. And similarly for node number 4 the metric you can see 11. And see the node number 5 because via D only all the packets goes. So you can see that how the connectivity to D, everything is 12, 11, 11, 12. So that's how the way the router from C to D, the path is with the heavy packets. So now you understand why there was a 39% packet loss because of the RIP network down. There was a packet loss involved in it. So now we can able to prove this through our this routing table. Now we can able to prove that through our Wireshark also. So now let me open some of the Wireshark packet capture files. You can see I've just opened one file here. This is the destination node. If you see the statistics there, so you can see up to some point of time, that is up to 60, somewhere around the 40, the packet got down, and because of the tear down link, or the link is down. So after some point of time it regains because the path, alternate path C to D is established. So this is for one of the packet capture that we can able to check it. Similarly, if we go with the node number, so route source node. So this is a source node. You can see the statistics here. So this is what the statistics. So source node generates the packet. So we have some additional values over there. The packet start with 1, and then you can see that again there's a downtime there because of the issue. So now it just open it, and now we will go to the node number, router number C. So we'll open the router number C, because via router C and D only the packets have gone. So we'll go with the router number C. But in C there are 3 things. So this interface 0, 1, 2. So 0 won't be the always be the loop back. We'll go with the 1 first, and router C1 the IO graph. So nothing was there here. So it is a normal packet transmission. So let us close this and go with the router number C with second interface. So when you go to the second interface, you can see the IO graph here. So via the second interface only, you can see somewhere at the particular time duration, after time duration number 70 or 80, you can see that there was a slight bulge in the packets there. So that means that during the downtime, I mean the other link downtime, so the C and D link took over, and then there was some packet exchange in this particular router C. So this can be verified with router number D as well. So router D also will be having the same kind of benefits what we can expect. So let us go into router number D with the first interface, router D. With second interface, I'll directly go with the second interface. See the packets there. So here also you can see that there was some from 80 to, I mean, so from 40 to somewhere around 80, we can see that there was a bulge there. And downtime, after the downtime, we can see that 110 the simulation gets over. So that indicates that this routing information protocol, which is belonging to distance vector routing, which we have seen through the routing tables and through the Wireshark packet capture. So that's all on this network. So thanks for watching. If you just like this video, please subscribe and